when one person shows up for the synchronous class. Did you try A6, and how far away along are you in A6, and do you want any help with A6? Oh, can a what do you mean by can collision have multiple values? As in, can you have multiple different? Can you have a collision in your hash table for different values? Absolutely, you can. I actually have one of those. I think I made a hash table last time around, um, and we can look at that if you want to look at that. In fact, I know what's going on in the exam. You mean using a linked list with the hash table, or having a what do you mean by like a linked list? All right, no problem. I have a hunch what you're going to get to, so let me just jump to it. $20. Is that the more recent one? Huh. Rect. Okay. What this I'm saying with this is, if you have a hash table and you try and if you put enough values in there, you will eventually get a collision. There's actually mathematical proof for this. It's called the Pigeonhole Principle. The idea is that if I have this hash table with a certain number of positions and I put enough values in, I will eventually run out of positions, or I will have two that are assigned to the same position. That is when I get a collision. Um, and so my hash table will say, put it in position 4, and another element of my hash table says, put it in position 4, and then you get a collision. And that's what we mean by that. Uh, so can it be more than two values? It will map to the same, two things will map to the exact same value eventually. If you put enough numbers in the hash table, it'll eventually two different numbers or two different elements will be assigned to the exact same place. It is similar to um, if you try and put, it's like every airline, I guess, eventually you run out of seats and two people are sitting on each other's laps, or one has to not to go on the plane, or you try and put 7 people into a car. Sometime someone's going to sit on somebody else's lap. Uh, and that's what we mean by collision. Essentially, they're saying, I'm going to go in this position, and there's already someone there. And so either you have them sitting on each other's lap or someone's staying out of the car. That's essentially what's happening here. So yes, you definitely can have two people go into the same position, despite having different values. They will map to the same thing. So I have, let's say every student gets a 3-digit student ID. Every student at Carleton gets a 3-digit student ID. Yeah, you're going to run out of spots after a while. We have way more than 999 students. As a result, what's going to end up happening is you're going to have two people with the same student ID. If you do that, you have a collision. If you randomly generate numbers between 0 and 999, you might get that collision well beforehand, two different students, two different numbers going to the same place, but you're going to have problems. So when we have assignments where they say put your last 4 digits of your student number, there's still a good solid chance with a large enough class that you have two people with the same last 4 digits of the student number. Uh, Yep. 3 values would be perfectly fine. It would happen. Yep. Let's do that. So I wanted to see where my most recent, this is the iterator one. Why is that so? Shouldn't be F20 though. Let's have a look at this though, just in case. Oh, I have iterators. Here are the bunch of topics I would talk about last week. So here I have, let me see here, student. Here's a big hash table that we're going to be dealing with, and sync hash. Sync hash is going to be a class. I already made it. Sync hash is I've added this string and this string and this string and this string, all sorts of strings I've added to this hash table. That's all I've done. Eventually, what's going to end up happening is no matter how many strings I put into this thing, eventually I'm going to have a case where two strings go to the same location. I think I actually have that right away, but let's find out. So let's go to sync hash. That's one of my classes. Let's see what my hash table does. I pass in a string. I need to get some ID, someplace where this thing is going to go. Oftentimes it's the pointer. If I have a pointer that I pass in, it says, hey, what's the address of that pointer? That can act as an ID. It could be your student number. That acts as an ID to uniquely identify you. There's some way of uniquely identifying each individual item. That does not mean that's where it goes in the hash table. It just means some unique identifier to the item. So here we have a name, and it's going into this hash table. It's going to generate some number, which is going to be the location where this string is going to be stored. So in this case, I'm going to take all of the various characters from the string, each one at a time. This is what I'm doing here, at least. Take each character one at a time, add the ASCII value to some character sum, just so it should be effectively a random number. So I'm just summing up the ASCII value for each character in the string. Then what I'm doing after that is I'm just randomly adding 17. Why? Because I can, right? I want something random. I'm going to do a random mod. I can get rid of these things. They're not actually doing anything at all. They're just what I was describing last time was I want random. I want this thing to be predictably random. I put something into I give you some random string, it will consistently find a place to put this thing. It'll always go to the same location, but I cannot predict what that location is. It will be consistent, but it will not be predictable. Much like if I whip a basketball the exact same way each time, it will go to the same place every single time. I can't predict what that place is, but that's what's going to happen. Let me read what you said. Okay. Okay. Yep. Yep. Hope that's not plagiarism in the assignment. No, you did in the labs, right? The hash table, just say comes from the lab. If you want to be clear, put a comment there saying comes from the labs. Good enough for me, right? The point of this is that I wanted people to play around with it, to try things out, not just blindly copy code. But if you got it that way, things are difficult enough in this course. I don't need to make it harder for you guys than they already are. And so in the case of when I give you an assignment or in the lab, you can use a lot of it. Yeah. So here's all I'm doing right now is I have a character, some of the characters, I throw it into the size of my hash table. So it's guaranteed to be some valid value between 0 and table size, whatever table size is. And that's what I should get. Let's make a collision happen. That's just fun. So hello world. Okay. I have multiple hellos. I don't want to use hello again. Let's do this. There you go. Should give different strings. Should give me a collision. Hello world by bold is capital. Okay. I'm going to remove the word hello. I'm going to add the word hello. Actually, let's add the word hello H. Okay. I'm going to compile all of this and see what the heck I get. So knowing what my hash table does, That's the reason why you want it as random as possible. Because knowing what my hash table does, I can make a system that sort of breaks stuff. Any permutation of a string, the string which is rearrange the letters, breaks stuff. It goes in the exact same place in the hash table. And that's what I'm trying to, I don't want to have predictable behavior, because what happens is if you're trying to break into a system, that's what you do. You throw the same thing at the same hash table multiple times. You can intentionally break their program, essentially. It comes up. It's one of the big things that they always worry about for hash tables. So ideally, you want sort of a random position. Here we go. Crap, hash table position was already filled. So hello world, LOH, right? That's where I get this crap. The hash table was already filled. Hello by world, hello was removed, LOH was added. I know into the same place because they have the exact same letters. I was generating my hash number based off of the ASCII values for each of the characters summed up. And so giving the exact same text string, but just the characters in a different order will cause me to put it in it will cause a collision. Let's do a third one, and let's do, so I'll do it as well, right? I'm going to have another collision. Collisions do not mean that it catches fire and explodes or anything like that. It just means multiple things are trying to go to the exact same position. Crap, crap. It's trying to go to the same place because they're the same characters, just in a different order. They're different strings. They're completely different strings. But the same characters, they have the same characters. Just how my hash table, my hash function works, it's taking the ASCII values, and so they're trying to be put in the exact same position, despite the fact the name is very different. Notice if I just use the first character of the text, I would not get this problem. If I wasn't summing up all the ASCII values, if I just took the numeric value of the very first character in my table, it's going to go to different positions. H is not the same as E, which is not the same as L. Right? Anything else that's going to do this kind of thing? Nope. So they're all presumably could go to a different location in the hash table. Let's just try that because I'm kind of curious what's going to happen. So here's my hash. What I want is, let's just comment this thing out for now. Char sum is equal to name.add 0. That'll do. I may have a collision somewhere else. So let's see if we get a collision somewhere else. Crap, hash table was already, so hello was removed. Oh, that's interesting. Oh, because I didn't remove it afterwards. That's the same as one of the previous pieces of text. What is at position 11, 26, 8, 15, 10, 4, 25, 11. How many different characters would I have? I would try a bunch of different characters to see if I can get it hitting the exact same ASCII value on the hash table. So in case you're wondering, this is what the problem was, where I had a collision, because I removed hello, which LO is not at the same place as hello, and that's why it has a collision there. What other things could I add? Hi, different word. Going to cause a collision. Nope, it's actually going to go in just fine. It's going to cause a collision if I do it up here. There you go. there's nothing. Everyone keeps on talking about hash tables as if there's something really crazy, and they're crazy in terms of the math when you get going with them. But there's nothing really crazy about the idea of it's just a lookup. It's a Dewey Decimal System. You have some kind of book with an author, a name, a publisher. I guess there's some other data as well. There's some way of mapping that to a series of numbers and letters that are in a particular order, and you just map those two things up. You map up the book itself to a particular unique number that you can look up in the library. That's all it is. It's a lookup. Here is what we have here. So after hello, capital hello, this hi gives me crap. Hash table position was already filled. It was already filled by hello, not hi, hello. They're very different, but they have the same character, first character in common. That's the reason we have a collision. Hopefully that answers your question. You can have multiple collisions. It doesn't do anything. It just means you either replace the old character with the new one, or you say, too bad it's already taken. I like the too bad it's already taken approach. You could, and I think I actually have this for the exam. Uh, you could, yeah, let me make sure I'm doing this right. For the exam, I think I can officially say some of the parts to it. I will be giving, let me make sure I'm doing it right and not screen things up. Otherwise, I have to make new questions. I should be giving a hash table that contains a linked list, meaning that if you, I really hope that's not, I'm not giving away anything, a hash table with a linked list inside of it. Because when you add elements, if I get a collision, I just have a linked list. And when I don't actually have a collision, it just goes to the same place and I just insert it in the linked list. So I get multiple, I have at each position is a linked list. And so if I had hi and hello, I have a linked list with two elements in it, hi and hello. And now I have to do a linear search through the linked list to find the element I'm looking for. That's slow. The hash table is constant time. It's a numeric value for a lookup. It's again like the Dewey Decimal System. If the Dewey Decimal System, more like let me think of a good example. Record shops. So you guys don't know what a record shop is anymore. Um, things like normal bookstores, things like comic shops, things like any place where you can buy a lot of, where there's a large number of items. There'll be some ordering, there'll be some organization. Like I'm going to the sci-fi section, and then once I'm in the sci-fi section, and then I'm looking for a letter of the alphabet, I find the letter of the alphabet, and then I just get a whole bunch of books with the author of that, with that letter of the name of their for their name. So Guy Gabriel Cave is an old sci-fi fantasy writer. So I look up Kay, I get all the sci-fi and fantasy authors that start with K. And I go through each book one at a time to find K. If that number of people with that last name in sci-fi and fantasy is too much, it's a big pain, right? I don't want to be looking through all of that. It's slow to go through that. Even if it's a small subset, it's still slow to walk through all of that. The hash table is just teleport right to where this location is. And now I'm going to look through this thing one by one, looking through all the books. So so Dan, can you unpack anything if there's anything I'm missing, or I feel like I'm rambling, but I may be rambling, I may not be rambling. I may not be rambling enough. All right. Sorry. You can also stop me anytime I'm rambling here because I don't see anything at all. Uh, So Marie Ethan, anything I can help you with when it comes to assignments? Do we need to go over sorting? Do we need to go over, there's a hash table, there's sorting, there's just objects in general, there's what is priority queue and how do they work? There's, I think I even have a priority queue in here. Priority queue. I also have a vector in here. So me adding a whole bunch of things to my priority queue, and then me reading off all of the things from the priority queue gives me my Dan, did you write Quicksort yourself? Because you shouldn't be writing Quicksort yourself. And there's no way in hell your priority queue should be faster than Quicksort. Quicksort is fast. Like if it's the same size data and it's a large enough data set, and if you have enough, so you have enough items, the one possibility is if your list was already sorted. If your array is already sorted, Quicksort theoretically can be slow. Theoretically, it shouldn't. What they should actually do is randomize your array. Honest to God, they do that. They'll randomize your array and then they'll sort it again. And that'll be fast. But theoretically, it can be slow if it's already sorted. But the priority queue should be it's painfully slow. Not painfully slow, but it's like bubble sort slow. Because it should be an insertion sort, effectively. It may not even be that. I set out to use the standard template library Quicksort. The standard template library has Quicksort, so let's have a look at it. If you wrote Quicksort yourself, holy crap, congratulations. That stumps professors, honest to God. I've written it numerous times. I've written it preparing for Google interviews and stuff like that. Tried to do it in memory Quicksort. That's difficult. But if you can do it, you've did it yourself. That is phenomenal, fantastic, great work. Maybe even just pass it in and just say, "Hey, I did it myself despite the instructions, and David said it was okay." Um, Here's Quicksort. So here's standard template library gives you things like priority queues, like here. This is from the standard template library. This is also from the standard template library. You also have functions that are predefined for you. This is actually C, really. And so I'm going to take my Quicksort. It's going to have some kind of base, which is the array I'm trying to sort. So I'm going to need a big old array. Let's see what I can do here. Can I int a nums size? Yeah, let's do it that way. That's a constant array. Will that do it for me? Hopefully it's going to be fine. All right, number of elements is 300. The size of an element is size of int. I need a function that is a comparison function. So that I do believe that this will actually work, but will that work? Eh, compare int. Whatever function called compare int. It's been a while. It's like months and months and months since I've done this. So when I do this, val1 minus. It might actually be the less than or equal to operator. So maybe it's a Boolean. And val1 is less than val2. It's a particular kind of for CRT non-secure search sort. I gotta look up what the heck that is supposed to be. Okay. Satisfies compare. Okay, three-way compare. Boolean compare type. There we go. Got it. So what the heck does all this mean? This means I'm going to write some kind of function that's going to take in pass by reference. I'm not allowed to modify the value. It's going to take two different data types, two integers in this case. It is going to then compare and it's going to return a Boolean. It's going to have a constant int ampersand, constant ampersand. It is allowing me to take any two values and comparing which one comes first or which one is before the other one. It should be comparing two integers, and I want to make sure that it's should be testing which one of those two if this is less than the less than operator. And then I need to figure out what the heck this thing should do. This is it's the function itself. Constant type 1, compare constant type 2, B. That's what it should be. This is just an and. It might be a pointer to the function itself. No, that doesn't seem to be the case. Let me have a quick look again. This is something I figured out for previous version of the class, when I think for the labs themselves. Where, oh, through a constructor compare. Compare. No, I don't want to compare. Let's just do this. Qsort sample. Yes, I do this all the time. Okay, integer comparison. Let's see here. Here's my call to Quicksort. It takes in an array of strings, string length, the size of each of the of a character string pointer, string compare, CRCMP. Do I have any other Quicksort calls? Here's an array of structs. Struct compare, string compare by place. Oh, it's going to take an int. Okay, constant. So these are void pointers. This doesn't make a lot of sense to me. And it's returning whether this thing is difference. Okay, let's do it that way. I didn't think it worked this way, so let's find out. Honestly, I don't like improvising this much, but all right. Compare int. I have something called compare int. I'm going to make it an integer again. Val. So if val1 is greater than val2, this is greater than or equal to. It'll be in reverse order if we do it wrong. And let's see where my qsort call is. And now I want to look back at my code. Here's my call, string compared by price. That thing should look compare by price. I have constant void pointer. This is weird. Here's it. Oh, there you go. In comparison function. There you go. So constant void pointer for two integers. Oh, we just got to cast it. That's fine. Let's just do that. Doesn't really hurt that much to do it this way. Okay. It's going to return this. It is a constant comparison pointer. So val1, val2. These are pointers. And I want to make this I want to cast this. So int pointer, constant int pointer. My val1, 2. Dereference my val1, my val2. Why is it not? Oh, reference. So it's going to get the integer value, subtract the difference, return that. Okay, and I say that seems to be all I need to do. It's pointers. But before I do anything, I need to set these values. So I'm going to have a for loop. 0, I at less than 300, I plus. I want to get some random, semi-random values. So I multiplied by 533 mod 300. Not going to be exactly perfectly random, but good enough for right now, at least. A. So the first couple times, but it's going to be 533, and it's going to be some huge number afterwards. So anums at position I is equal to that. Anums is already will instantiate everything. And let's do a printf statement afterwards. I'm just doing it this way, but all right. Let's hope we got something here. Boom. All right. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do we have any duplication anywhere? 44, 45, 49, 55. Oh, there's no real duplication here. Why isn't there duplication? I'm not even sure if I'd skip any numbers in here. That's freaking me out a little bit that I don't have any duplication in here. Just bear with me here for a second. Let's do that. I really want to see what the heck this thing looks like. Okay. Because I can't believe that we don't have any duplication in our numbers at all. That's just freaking me out a little bit. But I think it might be the nature of this. Let's see what I have. 0, 233, 166, 99, 32, 265, 198, 131, 64, 90, 297. It actually looks legitimate. I don't know if I have any duplications in any of these numbers, but that's what I'm getting right here. It seems to be, it's a random number, but it's filling in all the actual numbers in the number system between 0 and 299. Seems to be what is happening here, which a little surprising, but I'm okay with that. I'm just really kind of shocked that I don't have duplication here. Yeah, no duplication. There's just, we're filling in every number, but it's not sorted at first. And then I call sorting, and then I've now sorted all of those numbers after the fact. So I've sorted all the numbers, and this is what I get as a result. And if I put the timer on it, it should, the actual sorting, don't do it for the printing, but the actual sorting should be faster, especially with a large enough set of numbers that the array, the speed in which this thing sorts things should be vastly superior to the priority queue sorting or bubble sort or insertion sort or any of these other sorts. So what I had to do, I had to figure out, I had to make a function that allowed me to compare to the elements in my array. It doesn't have to be in an array. It can be anything. It just has to be how you can compare elements from a collection of different, an iterable collection of values. So technically, you can have it so a linked list gets sorted because it has an iterator to go through it, and it knows how to sort it. That's the point of this. Somebody wrote Quicksort. It works for any kind of sortable list as long as you can compare values. It works for any sorted list. That's pretty crazy in my books, at least. Not a waste. Sorry, but I appreciate the fact that I wish I could have stopped you from doing that. I'm sorry. If check the instructions, and by the way, pass in what you have. But check the instructions. If I don't say, hey, by the way, use a standard template library, then that's my bad. But I was pretty sure I say use a standard template library for Quicksort or use qsort. Because that's what we're testing. If you can do Quicksort, you can do a lot of stuff. You should be extremely proud of what you were able to get through. It was not meant to be a 5-hour slog through stuff. The slog would have been your other sorting algorithm, but Quicksort, yeah. Sorry. Now, technically, I would say since you're not using Quicksort, that counts as your own sorting algorithm. It's just a badass sorting algorithm, so good for that. Yeah, so Maurice, you're absolutely right. You want to do your own sorting algorithm? You got one. If you didn't already do another sorting algorithm of your own, you can't make up your own. Essentially, no matter what you come up with, it's been done before. So if you may kicksort yourself, great, use it. Ah, well, at least your bubble sort's slower than your quick sort. Okay, nice. Because quicksort is, quicksort's badass when you do it right. If you do it in a non-efficient way and you're transferring things to arrays and stuff like that, it's slow, but it's a crazy algorithm. It's pretty awesome. All right. Can I unpack anything, or do people want to see me try and do quicksort? I don't know what you. That might be even worse. That might be just sad to see me try. You don't want to see me try and do quicksort on the fly without any prep, because the actual speedy algorithm is not the one you would naturally natively do. The naive approach is to make each time make two different arrays, sort the numbers based off of the pivot into two different arrays, and then call quicksort on each of the two different arrays. But now the value in the middle is sorted. The pivot is always in its final place after you've done that sorting, and then you just keep on redoing it. It's a divide and conquer algorithm. But the cool thing about it is you don't have to make new arrays. You just need to shift stuff around. And if you're really good with your bookkeeping, you can take one array, sort it in place with the same memory, as long as you know where the sorting algorithm, where the smaller group starts and ends, where the large group starts and ends. You can sort it in place, and it's really efficient and really powerful, really error prone, but it leads to a really efficient algorithm. So what's the comparison function for a quicksort? It's going to be different for each group. It is what we talked. I think you just came in right now, so that's fine. It is a function that you can write that allows you to compare values. So here is I just wrote a function called compare int. By the way, I think we also talked about in the lab, or I give an instruction of what the heck that looks like. Please say I do, because that's my working memory on this one is I've told you what the compare function sort of looks like. Maybe I'm wrong. So I've been wrong about a lot of things. So I don't want to make a firm stand that I gave you all the information you need, just in case I'm wrong. So here's what the compare algorithm would look like for comparing an array of integers. I just get a void pointer. It's the pointer to the data that I'm looking at any given time. This is what I'm, at least we got getting going off the ground. It's a constant void pointer. So I'm not allowed to change the void pointer. It's a pointer to some data somewhere. Is it an integer? I don't know. Is it a character array? I don't know. It's something. I have a pointer to one of the values. I have a pointer to the other value. So this value here, this number here, and this number here. It's not the values themselves. It's where they're located in space. Okay. Then I say, okay, I'm going to actually make it an int pointer. I know this is an integer. I know this is an integer. Why? Because I made the array of integers. I know they're arrays of integers. I know these are integer pointers. And then once I have an integer pointer, I say, hey, by the way, dereference it, make it just a normal integer. This normal integer minus this normal integer, which comes first? So if I take the difference, if this is positive, it means value 1 is greater than value 2. If it's negative, it means value 2 is greater than value 1. And that's what if I did the other way around, let's see what happens if I do the other way around. What the heck? So I just have the value at those pointers. That's all I've done here. And took the difference. Boom. Largest number to the smallest number. Exact reverse order. And so you go, how do I know which order? You write this and you say, what order did I get? Oh, I have it in reverse order. Switch the 2 to a 1 and the 1 to a 2. Done. It's But the idea is I can't pass in a value in here because I don't know what kind of data I have. I could have a character array for all I know. I could have an integer, I could have a struct, I could have this, I could have that. I could have any number of different kinds of data structures. So instead, I just say, give me the pointer to one of them, give me a pointer to the other one. Now let me figure it out. So yeah, you can go ahead and steal this. Why? Because I stole it myself. So say though you stole it from me and that was stolen from online. So that's fine. You're not supposed to, half this stuff you don't, you figure it out by looking up something online. That doesn't mean, that's not the same as on an exam when we say use this thing or do this thing, because one is showing understanding, the other one is showing you know how to use the syntax. Congratulations. I don't know what the syntax is. I can look up the syntax. You can do that on the exam. That's fine, because it's syntax. It's like what's the English word for this? Well, look it up. How do you spell onomatopoeia? I don't know. Look it up. That doesn't mean you can't write. It means you don't know how to spell onomatopoeia, right? That they're radically different. No one says George Steinbeck, he can't write. John Steinbeck. Steinbeck can't write at all because he doesn't know how to spell onomatopoeia. No, right? It's spelling. His grammar is not that great, right? The ability to write is radically different than the ability to know your grammar rules or to know how to spell. We're talking about spelling here when it comes to how the syntax works. That's not the same as understanding the problem. Anyone can look up how the syntax works. Understanding the problem can't really be taught, and that's the thing we're really trying for. Because when you stop using C, the logic still works when you go to Python or you go to any other language. That's where the line in the sand is. All right. Can I unpack anything else? I've just been rambling on a little bit, but other than that, are there things in assignment 6 that were confusing? Covers a lot of material. Now I have a sudden inkling or sudden urge to write Quicksort as fast as I can. Should. They also merge sort, but that you cannot do that in place. Okay. Thank God. Which is a hash table in the main of CPV for the sorting. Oh, can we sort the hash table? Hash table doesn't sort things at all. And if you move things around, and if you move stuff around in the code, like you move stuff around, what's going to end up happening is the hash table is going to break because it's not the. If you move it to a different position in the array, suddenly the hash table is looking for the wrong thing. It's having a Dewey Decimal System and then assuming the library is in alphabetical order or moving it into alphabetical order for all the books. If you have a Dewey Decimal System and then you suddenly move the books around into alphabetical order, you're going to go to the wrong position in the library. Okay, just the code instead of creating a CPV to test the hash table. Well, I'm sorry, I'm missing something here. Could just hash table in the main CPV for the sorting. Oh, can we, as in, do we need to have a separate class? I mean, this hash table, it's an object, it's a class. I made it into a class instead of having it just a struct. So I was trying to demonstrate object-oriented programming principles as a result. That makes sense? So I'm using the hash table in here. I'm using a hash table, but the actual object itself, I'm making a new object, a new hash table object, and then I'm adding crap to it. Should also be deleting it at the end. Let's make sure I delete that thing. I forgot to delete my object. Why do I need to call delete? Because I called new. If I call new, I better sure as hell call delete. That's just a general rule that we have. If I make a new thing, if I call new, I got to call delete. It's dynamic object allocation. It's just like a dynamic array. If I make a new array, I call malloc in C terms. If I call new and an array in C++ terms, then I need to call delete at the end. We also don't have to stick with this. We can go to anything, including inheritance if you wanted to, but maybe you guys are sick of inheritance. I have a potential topics. Iterators, if anybody wants to look at an iterator. I have an iterator ready to go, I think. Iterators. All right. So iterators are sort of weird and nasty and ugly and terrible, and they smell bad. What is an iterator? An iterator is just, I'm going to bring up the old code from before, just what I've used before. Okay. All the iterator is if I don't have an iterator, what do I need to, let's look at my linked list.h. If I don't have an iterator, what do I have? I have this linked list. And when I want to add something to my linked list, I can add some data. That's fine. I can insert at the front. I can insert at the back. That's great. Okay. So far, I just have this big black box that stores stuff. That's what I want. I don't want to know how the sausage is made. I just want to have some sausage, right? I don't want to know how this thing's put together. I just want this tool, this thing that holds data for me. In case you're wondering why I say this, do you know how a vector is formed? No, you don't need to know. Do you know how Quicksort is working? No, you don't really need to know. Right? Do you need to know how priority queue works? No, you don't need to know. That's why we do it, because therein lies madness. If you had to understand everyone else's code, you'd cry. If you thought reading my code was bad, imagine reading everyone else's code on top of that. So inserting at the front, inserting at the back, all fine. What if I want to insert in the middle? What if I want to find a particular element in my array? Now, if you say find this particular element, I already know what the name of the data element is. That's not really useful. If I just return the data element, I would be like, see, the thing I passed in is a thing I got. Congratulations. It's useless. What if I want to remove it? Well, I don't know if I want, what if I want to print everything out? What if I want to get a particular element at a particular place in my array? That's what an iterator is for. The iterator, before this, I would have to return an LL node. And at that point in time, I'm saying, by the way, this is what we're dealing with. If I call this super storage 5000 instead of linked list, you should be completely unaware that I'm using a linked list. It is a linked list. Everything works the same. It's just called super storage 5000. I don't want you to know how it's built. It could be an array. It could be a linked list. It could be whatever you want it to be. And it should still operate exactly the same. I don't know if I have demo iterator. I think I have demo iterator here. Iterator. There you go. SA iterator. Here is my secret array class. This is my, I give this as one of the videos if you want to have a look. Here's my secret array class. It is an array. It has a number of elements. It's just an array. It's just an array like all the other arrays we've ever used. I add to the array. I take away from the array. I add elements to the array. It's just an array. If I wanted to say find a particular element in my array, I want this thing. I don't want to know that it's an array or if it's a linked list. I just want some structure that stores stuff. If I don't have an iterator, I have to let you know that it's a linked list or an array or a tree or something else. I don't want anyone knowing that at all. So the idea is I have a data structure that I can get individual elements for, and I need some way of going from one part to the next part to the next part to the next part. That's the iterator. The iterator is just another abstraction, so I don't know how things are built. I magically add stuff to the array, to the data structure. I magically remove things from the data structure. I magically walk down the data structure, and I'm completely oblivious to how this thing works. To the point. So let me see my main. Here is my linked list. I have a whole bunch of data items that I'm going to add to it. It's just types of data being added to the linked list. I add a bunch of data to the linked list, print the linked list. I check to see if the linked list is empty, just in case. And then maybe I print everything off using it. I have an iterator here. Get the start of my linked list. I print out all of the elements in my linked list. So I get the value at the iterator position. I move the iterator position over one. I just say, you go to the next one, go to the next one. The iterator is like my finger on on the page, or what, like or a bookmark. It just points or refers to what I am currently looking at, and I can move it forward or back. I don't jump around. I just go next one, next one, next one, next one. So I'm counting the elements. I'm using my finger and doing this kind. Let me see. There you go. There you go. Doing this kind of thing. When I'm counting things, I use my finger to count. That's what an iterator is. That's all it is. I go, and the next one, and the next one, and the next one, and the next one. I check to see if there is a next one. If there is a next one, I get the next element. I get the value that's being stored there, the data. I print out the data until I get to the very end. That's all I'm doing. This thing is pointing to the front of my linked list, and then the next element, the next element. It's just pointing. And then I can remove a bunch of stuff here. The interesting thing about an iterator, and this is also, again, in the video, just in case, I know if you've watched the video, you think I'm just repeating myself. Let's see if I have anything else in here. That you don't need to know it's called an SA iterator or anything like that. It's just an iterator. All the functions look exactly the same. All the functions act exactly the same. In fact, I just changed 2 pieces of code in total. If I didn't tell you the name of the function is SA iterator, just called iterator, and the other thing called data collector, you wouldn't know. You would just think it's just an iterator, the thing that iterates or walks through my array, and data collection. So everything compiled. Everything works as expected. Here's what the printout of all my things in my iterator art look like. With me so far? So the secret array has these particular elements in there: 17, -2, 9, 21, 0, 17, -2, 9, 21, 0. And then I do a bunch of stuff with it. Okay, 17, -2, 9, 21, 0. Notice the output looks a bit different here because the function I'm calling is actually different. But the iterator gives me the exact same data. Everything's stored the exact same way. It looks, smells, acts exactly like it did before, except one is using a linked list, one is using an array, and you don't change squat. It just stores numbers. The iterator allows you to hide the fact of how this thing's being built. So we just finally replaced our 11-year-old car or something like that. A Mazda 6, very good cars, but battery was dying because of not driving it, and it sounded like a tractor. We just bought an Accord hybrid. You cannot tell, or you can barely tell, that it's a hybrid. It looks like an Accord, acts like an Accord, shaped like an Accord. Everything about it is like an Accord. The only real difference, there's a slight difference in terms of how it sounds, and that's about it. Ideally, you wouldn't even have that. Other than the improved fuel efficiency, it should look, act, behave exactly like an Accord. It just happens to be a hybrid instead of a pure gas car. That's what we're looking for. You can't tell the difference. You can't tell anything between the previous and the new at all. But maybe one's more efficient. The functionality is exactly the same. You don't know how this thing is built. You don't have to know how all these things come together. You just want it to come together. To take the final exam, you don't want to know how I designed the final exam or how many questions I go through and how many false starts I have or how much dead code I have and all this other stuff. You don't want to know all the various versions of the exam. You just want the exam. Well, maybe you don't want the exam, but you don't want to have to worry about all that stuff. You have to take the exam, so you just want the exam. You don't want all the other nuance and details. The iterator allows you to go next, 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 next without worrying about, so you don't have to worry about that. So let's actually look at one. Here's my demo iterator. A bunch of getter methods. I can get the next. I can check if there is a next. And I can check to see if two iterators are equal. So I know if I'm at the front or the end. That's the reason for that. Are these two iterators equal? Am I at the point in my linked list or my array where, I'm saying I'm going to insert it at this point. I have my iterator, it walks down until I get to the other iterator that is pointing at the thing I wanted to point at. So when they match up, then you can stop, for example. So that's what the point of an iterator. These are just general functions for an iterator. Things that every single thing that's going to point to something does. We could have something like get element index or something like that every iterator had. And a linked list would have an index, and an array would have an index, and a tree would pretend it has an index, and it's all good. It all works the same. And I should be able to get the value at the iterator. I don't want to. No one should know that there's even a thing called LL node. It should be completely invisible to the average user using this system. They know they have an iterator. They know it, and the only reason the standard template library works because they have iterators. I don't go to element 27 in my vector. I go to the next element in my vector. So the iterator class, here's my iterator, has next gets the next element, or moves in one position over, just moves over. Does it have a next element? So I don't want to go next over and not have anything there. And I check to see if two things are equal. And I also get the value. This is what it looks like. LL iterator can know all about the nodes and all this kind of stuff. It's wrapping up and hiding things. It's hiding how things are built together. So it knows about an LL node. You can pass in an LL node and can make an iterator that way. Because when I make the iterator, the linked list is going to make an iterator for me. I should be able to get the next. Getting the next involves getting the current node. Do I have a next element? If I do have a next element, I set the thing I'm pointing to the next element. Does it have a next? Well, is the current node not equal to null? Does it have is a next after the current node is not equal to null? This is just normal linked list node stuff, but I'm hiding how it works and just having this idea, this concept of an iterator. Is there a next one? Well, I'm pointing at the last element, so no, there is no next one. I'm rambling on for a bit, so let me see if I can unpack any part of this right now. Does the concept or the motivation behind an iterator make sense? Maybe that's more aimed at Dan because he asked for iterators initially, but at the same time, anyone else, if you're confused, please let me know as well. You see one other thing if I can do that. So here's a linked list iterator. Here is the secret array iterator. Secret array iterator, linked list. That does okay. Linked list iterator. looks like this, has a next, next has next equals get value. Next has next equals get value. They have the exact same functions between the two of them. That's the point. If they have the same functions, they act the same, look the same, behave the same. If it looks like a duck, quacks like a duck, then it's a duck. And so we have two things that look, behave, and act exactly the same as each other. And therefore, no one's the wiser how things are built underneath the hood. But for this secret iterator.h, I have a bunch of data, an array of data. I have the elements. Let me see here. The number of elements in total, the current index. Why do I have this other? Oh, that's just the data itself, I think. But I should have access to the data itself. I didn't even need the secret array in here. It's just an array that I have in here. Here is the linked list, array of linked list data that I just hooked up to. What is this going to do? Yeah, because they didn't want to use a friend class. That's what it was. Okay. The idea of an iterator is that I don't know how it is built. And I can just go next, 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 next. I got a yes iterators and then nothing afterwards. So I don't know how confused people are. All right. Sure. Hit me. What's your little question about pointers? Double pointer array. Well, oh, you mean a two-dimensional pointer array, right? Not a double array of pointers, because then it's doubles. Yeah. So a two-dimensional array of pointers of integer pointers. Okay, yeah. Of two-dimensional array of integers. My array is a two-dimensional array. So if my array is a two-dimensional array and you dereferenced it, it's going to be the first array of my array. Okay, and this would point to the very first array of my array. Let's see if I can give an example. Uh, that's iterators. I want to see where the last thing I was working on was for this. Eesh. All right, make it fun. It's going to be source. Okay. And, and so what you're saying is something like 1, 2, 3, 4, 5, 6, 7, 8, 9. Spacing is going to go off. Oh, let's go 9, 1, 9, 0, 1. Okay, there you go. So what you're saying is a two-dimensional array this is a 3 by 4, 3 rows, 4 columns array. So I would have int array. So let's do a double array. Is equal to int star size 3. So it's a new array of integers of size 3 in this thing here. It's an array of pointers to integers. All right. And within my normal handy dandy for loop, because I'm going to change those numbers around afterwards, maybe in my handy dandy for loop, I'm going to have int, let's do arrays of size 4. And let me see here. Close this for loop. So what you're suggesting is int is array equal to that. So what this would do is, what's my array? My array is this whole thing. In fact, what I should have is, let's do that. Okay, we're making a brand new array. That's going to be that. I'm going to make a for loop in here. And j is equal to 0. J is less than 4, j plus plus. And what we have is I times 4. Okay. So nums at position j is equal to I times 4 plus j. Probably wonder, what the hell am I doing there? This is just going to go 0, 1, 2, 3, 4, 5, 6, oh, way up, and then keep on going. So it's going to give me this behavior right here. But instead of 9, 0, 1, 2, it's 9, 10, 11, 12. So let's put that 10, 11, 12 in here. And it's also going to be 0 base. So you can also increase by 1 if we wanted to. Plus 5. All right. That's all this thing is going to do. So my very first array that I have here, I'm putting a bunch of numbers in here. The name of the array is this. Okay. So this is going to go to the very first row and say, what is in the very first position in that array? That's dereferencing my pointer to this. I am pointing to this entire array here. The entire array is consisting of a pointer to this thing, a pointer to this thing, a pointer to this thing. So 3 different pointers. That's what my array is, 3 different pointers. Let's also do I have an array that's pointing to this thing. I have a pointer to this, a pointer to this, a pointer to this. When I call my array, it is the pointer to this entire data structure. If I dereference it, it's just the pointer, the very first pointer, this thing here, which is pointing to 1, 2, 3, 4. So his array is a pointer to 1, 2, 3, 4. That makes sense? In fact, we can actually print this off. And for I shouldn't be using these hard-coded values, but by the way, like 3 and 4, that's a bad idea normally, but the out, and we're going to put in our a my array at position I, and then at position j. All right. So what is this going to do? This is going to go through, find the first row, and then the second row, then the third row. It's just a pointer, these pointers here. Then from those pointers, I'm going to go, it points to this array. I'm going to go to the individual elements in here, print off the value in there. And that's what I'm going to do a whole bunch of times with this 2 for loops thing. Aren't you? Boom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2, an array of arrays nested together using our new techniques. I like this new syntax more than the old malloc crap that we had before, but that was C. This is C++. Right. We're getting a bit late. I know I talk a lot, but I also know you guys have other things to do, I'm sure. I will also want to make sure that you're feeling comfortable with this, though. So anything else that I can cover or help out with? All right, nice. Well, I'm hopefully that was somewhat informative and useful for you. And I will hopefully we'll have another catch-up class on Friday, and then we'll go from there. All right. Thanks, everyone.